So before we start today's lecture, I would like to answer the question 5 of the practice questions for last week so that you have a recap of what we did last week. So the question says, the demand curve for a good is given by Q equal to 10 minus 0.5p, and the total cost function is given by TC equal to 3q minus 8q squared plus 20q plus 2. So the question says we should find A, an expression for the profit function of the firm in terms of quantity. B, we find the level of output that maximizes profits. C, we find the price. Then D, we find the maximum profit of the firm. So first, we'll have to extract what is given in the question. The question is given a demand curve and the total cost function. So we are given the demand curve. Q is equal to 10 minus 0.5p. Then total cost is equal to QQ minus 8q squared plus 20q plus 2. The first part of the question says we should find profit function. So A, we know profit is equal to total revenue minus total cost. So we know total cost, we have to find, so this is total cost, we have to find total revenue. We can find the total revenue from the demand function. So we know total revenue is equal to price times quantity. What we have to do is, I've told you last week that before we find total revenue, we have to first make P the subject of the demand function. If P is already the subject of the demand function, then you don't have to make P the subject because it's already the subject. In this case, Q is a function of this demand, is the subject of this demand function. So what we have to do is to make P the subject. Making P the subject means we are going to write P is equal to everything else. Okay? Okay. So in order to find total revenue, first make P the subject of the demand function. So in this case we have Q is equal to 10 minus 0.5p. So we have to bring P here and send Q there. So we have 0.5p is equal to 10. So this is plus, if you cross the equals and it becomes minus, so you have minus Q. And remember, we want P, we don't want 0.5p. So you have to divide through by 0.5. So whatever we do to the left hand side, we do the same thing to the right hand side. So divide here by 0.5. So this 0.5 cancels this 0.5. So you have P, then divide this side by 0.5. So this will be P is equal to, so this means 10 divided by 0.5. Then we have Q divided by 0.5. So this is 10 divided by 0.5 minus Q divided by 0.5. So we have P is equal to, so when you are using our calculators, this is 100 divided by 5. So that will give us 20. Okay? So this is 20 minus the coefficient of Q is 1. 1 divided by 5 will give us 2Q. So this becomes price. So we can name this equation 1 because the question says we should find P. So when we are able to find Q, we just substitute it there, we're able to find P. So now, our total revenue, we know is equal to price times quantity. So this is equal to, so price is equal to this whole thing, right? So we substitute 20 minus 2Q. So this is 20 minus 2Q times this Q. And we know how to expand functions. So Q multiplies this and Q multiplies this. So we have 20Q minus 2Q squared. So this is our total revenue. So we have total revenue function, we have total cost function. So if you substitute those two functions in the profit function, you can find the profit function. Okay? Okay. So by substituting pi, which is profit, is equal to total revenue minus total cost, and this is equal to total revenue is 20Q minus 2Q squared, and because this is minus, we have to put the profit function in brackets. So we have QQ minus 8Q squared plus 20Q plus 2. So profit is equal to 20Q minus 2Q squared. We are expanding this, so minus affects everything in brackets. We have minus QQ plus 8Q squared minus 20Q then minus 2. So we can simplify this. So I want to write the highest exponent first. So I have minus QQ, then I have Q squared, so this is 8Q minus 2Q squared, so I have plus 6Q squared. I have 20Q minus 20Q, so that will give me 0. Then I have minus 2. So this will give us the profit function. So this solves the first part of the question, which is the A part. So I can name this also equation 2. So the second part of the question says we should find the level of output that maximizes profit. So that's a function. If you want to so we should find the output level that maximizes profit. So we just apply the first and the second order conditions we learned last week. So B, finding the output level that maximizes profits. Okay, so we know our profit function is Q minus QQ plus 6Q squared minus 2. So the first order condition states that, so we should state the first order condition. The first order condition states that for any maximum or minimum point, if we differentiate this function with respect to quantity, we should equate it to 0. So what you have to do is differentiate this function. So we have d pi dq is equal to, so bring the exponent down, so we have minus 3q, you subtract 1 from the exponent, so we have square, plus, so we bring this exponent down to multiply this, so we have 12q, we subtract 1 from this, so we bring right to the power 1. and the condition states that we should equate this thing to 0. So this has become a quadratic equation. So this implies that minus 3q squared plus 12q is equal to 0. We can try to multiply through by minus 1. We can just do this. So we can factorize minus 3 out. So 3 is common here, 3 goes into 12. Then q is common here, q is common here. So what we do is factorizing minus 3 out. So we have minus 3q. So when we do that, it's left with 1q here. Then minus, remember we are factorizing minus out. So minus 4. This is equal to 0. So if you want to expand this is minus 3q squared, we give you this, then plus 12q. So this implies that either minus 3q is equal to 0 or 4 minus q is equal to 0. So minus 3q is equal to 0. This implies that q is equal to 0 or q minus 4 is equal to 0 and q is equal to 4. So that's the first order condition. So the first order condition is a necessary condition. So at this point, we don't know whether this maximizes profits or q is equal to 4 maximizes profits. So we have to apply the second order conditions. So second order conditions. So before the second order condition, we have to find the second order derivative of this function. So this is the first order derivative of the profit function. So we have d pi dq, which is equal to minus q squared plus 12q. So the second order condition is to differentiate this function again. So that is the 2 pi dq squared. So again, we bring this one down, so we have minus 6q, then plus 12. So we'll try to find out whether this maximizes profits or that one maximizes profits by substituting q is equal to 0 here, by substituting q is equal to 4 here. So first, we do when q is equal to 0. So when q is equal to 0, we have the 2 pi dq squared at q is equal to 0 is equal to, so we have minus 6 into bracket, so q is equal to 0 there, plus 12. And this is equal to 0 plus 12. So this is positive 12. This is greater than 0. Therefore, since the second order condition is positive, we can conclude that q is equal to 0 minimizes profits. So now test for when q is equal to 4. So when q is equal to 4, we have the 2 pi dq squared at q equal to 4 will be equal to, so we have minus 6 times 4 plus 12. So this is minus 24 plus 12. So this is equal to minus 12, which is less than 0. So the second order condition states that when q is equal to 4, the 2 pi dq squared is negative, it's less than 0. Therefore, we can conclude that q is equal to 4 maximizes profits. So in order for the firm to maximize profit, it must produce output 4 units of the output. So that solves the second part of the question. So now the third part of the question says we should find the price at which the goods should be sold in order to maximize profit. So remember when we did the first part of the question, we were able to write P in terms of quantities. So all that we have to do is to substitute the profit maximizing level of output, which is Q equal to 4, into equation 1 to find the price that maximizes profits. So see, in order to find the price level, substitute Q is equal to 4, which is the profit maximizing level of output, into equation 1. In equation 1 we have P is equal to 20 minus 2Q. So we have P is equal to 20 minus 2 times 4. So P is equal to 20 minus 8. So P is equal to 4. So in order for the firm to maximize profits, it should produce 4 units of the output and has to sell it at a price of 12. So that also solves the C part of the question. The last part of the question was to find the profit, the maximum profit. So in finding the maximum profit, substitute Q is equal to 4 into the profit function, which is equation 2. So in equation 2 we have pi is equal to minus Q cubed, right? Plus 6Q squared minus 2. Yeah. So this is equal to minus 4 to the power 3 plus 6 times 4 squared minus 2. And this is equal to minus 4 cubed is 2 to the power 6. 2 to the power 6 is 64. So 4 times 4 times 4 to get 64. 4 times 4 times 4. Yes. So minus 64 plus 6 times 16, 96 minus 2. And this is equal to 96 minus 66. So our maximum profit is equal to 30. So this is max profit. So max profit is equal to that. So that solves the practice question 6. So you continue to try your hands on the other questions and let's see how it goes. So we'll continue with what we are supposed to do today. The other thing that I will have to show you, but we are not going to practice them. If in a normal class session, I would have taught you those things, but because of circumstances beyond our control, I will leave it like implicit differentiation and stuff. But today, we'll talk about partial differentiation. Partial differentiation. So, partial differentiation. Partial differentiation. So there are two things you have to remember. First, what we did last week, we have just a function of one variable. So we have y is equal to a function of s. And the partial differentiation, we have a function of several variables. So this is function of single variable. So y depends on only s. When you have s is a function of f of s1, s2, up to sn. So y, z doesn't depend on only s1, but it depends on s2, s3, s4, s5. So you have several variables. So this is function of several variables. Functions of several variables. An example is when you have a demand function. Economists say demand is a function of the price of the good itself. It's a function of the price of related goods. So if you want to buy ideal milk, you look at the price of pig milk, carnation milk, and that type of milk. It depends on your level of income. If you don't have resources, demand is actually your willingness and ability to purchase a product. So if you don't have income, you won't have the ability to buy the product. It depends on taste and preferences. It depends on advertising, expectation about prices, expectation about income. It depends on so many things. So this is an example of a function of several variables. Demand doesn't depend on only the price of the good, as this may be the case. So when we had y is a function of s, we use differentiation to test to find out how changes in the s, the variable s, affects our y. So when we have functions of several variables, what we are coming to do is we want to find out how changes in s1 affect z, holding all other things constant. What we cannot do is we cannot find changes in s and changes in y together and find their effects on z. We will not know whether higher portion of the effect is from s1 or from s2. So what you do is, if you are finding the effect of changes in s on z, we hold all other things constant. So one thing you have to notice, you know from previous lectures, so last week, so note, we know that if y is equal to f of s, and is equal to s to the power n. So this was known as the power rule. dy ds is equal to, so bring n down, s n minus 1. Okay, so we use this one and the calculus of several variables, so nothing changes. If you are differentiating, you bring the exponent down and subtract n from the exponent. And also note that if you differentiate a constant, you get 0. So we had if y is equal to k, where k is constant. I showed you that dy ds is equal to, since this doesn't depend on s, it's the same as, so this is the same as y is k s to the power 0. So 0 comes down, then everything becomes 0. So if you differentiate a constant, you get 0. So these are the two things will apply in the calculus of several variables. So you note, as I was told, if you have y is equal to s to the power n, when you are differentiating, you bring n down, then subtract 1 from the end. So when you differentiate any constant, you get 0. So suppose in partial differentiation, so if you have z is equal to f of x, y. If you want to differentiate, find changes in how changes in x affect z, write dz ds. So this is what we call partial differentiation. You see, this is not like the total differentiation where we say last week. This d is different from, so this is like an inverted or s stand sideways. So this is change in z as a result of change in s. So when I define change in z as a result of change in s, we hold y constant. Then if you want to find how changes in y affect z, write dz dy. So this is change in x, change in z as a result of change in y. So when we want to find changes, how changes in y affect changes in z, we also hold x constant. So example, suppose suppose z is equal to s squared plus 3y. Suppose z is equal to s squared plus 3y. We want to find changes in s on z and changes in y on z. Remember I said if you want to find dz ds, you have to hold y constant. So here dz ds is equal to, so this depends on s, so we just apply the rule of differentiation. We bring n down and subtract 1 from the exponent. So we bring 2 down, so we have 2s. Subtract 1 from this, but I don't write to the power 1. Then plus, so since there's no s here, it means that this doesn't depend on s. So this is a constant. So like this, you have y is equal to k. There's no s here, so this is a constant. If you differentiate every constant, you get 0. So this implies that, so plus 0. This is because there's no s here. There's no s here. Okay. If you want to find dz dy, it means we also hold s constant if you are differentiating with respect to y. So here there's no y here, so this is a constant. Remember, if you differentiate every constant, you get 0. So we have 0 plus, then this is 3y. Remember how to differentiate something like this. So this is 3, this is y to the power 1, so 1 comes down, subtract 1 from that. So we get the coefficient of y. So this is equal to 3. That's all. Maybe I'll do more examples. Then you get it. Wow. So example 2. If z is equal to, so this is equal to, so 2 times 3 will give us 6. So we have 6 x squared y squared minus 10x. So this is dz dy. I've done 3 examples. I hope I'll give you some questions to try your hands on and see if you're able to get it. But the most important thing is, if you're differentiating with respect to x, y is constant. If you're differentiating with respect to y, s is constant. So just apply the rule that we did last week. So here, this one was when we have calculus of a single variable. So here y was just a function of x. So if y is equal to k, which is a constant, x to the power n, the y ds was equal to, so k is constant, so we just ignore it. Then we apply the power rule, so bring n down, s n minus 1. Okay. So if you have z is equal to 2 squared y cubed minus 10sy plus 2s plus 12. If you want to find the z ds, we are differentiating with respect to x, so y is constant. So it means that this 2 is a constant, is a number. Y cube is also a constant, so we bring them out. So like the way we brought k out, right? Then we differentiate this s squared. So like s to the power n. So here our n is equal to 2. So this holds into y cube acts as k, right? Then we bring the 2 down, so 2x, so 2 minus 1 will give us 1. We don't write to the power 1, so that's why I just wrote 2x. Then minus, we are still differentiating with respect to x, so y is still constant, so minus 10y are constants. They'll just differentiate s. And last week I told you if you have y is equal to s, dy ds is equal to 1. Okay? So we have 1 here. Then plus, so if you have y is equal to ks, dy ds is equal to the k. So 2s, so we have 2, we differentiate s, just get to 1. Okay? Plus, if you differentiate any constant, you get 0. So plus 0. Then we can simplify them. So this time this will give us 4y cubed s minus 10s times 1, you just have 10s plus 2 times 1, you get 2. Now, if you are differentiating with respect to y, dz dy is equal to, so this, in this case, s is now constant. So 2s squared will act as our k. So bring them out. Then we'll differentiate y cubed. So like s to the power n. So n comes down, so 3 comes down, y, then 3 minus 1 will give us 2. So that's how we have 3y squared. Minus, so again, 10s is constant. So 10s, we differentiate just where we have 1. There's no y here, there's no y here. This is a constant, this is a constant. Get 0 and 0. Then, when you simplify this, so this is 2 times 3 will give us 6, s squared, y squared. Then we have minus 10s. Okay. So last week we did calculus of, we did second order derivatives. So in this case too, you can find second order derivatives. So I said when we have z is a function of x and y, we can have dz, ds, we can have dz, dy. So dz, ds is a change in z with respect to changes in s. dz, dy is change in z with respect to changes in y. So you can find second order derivative of this. Remember when we have y is equal to f of s, we had dy ds, then was the first order derivative, We have the 2y dx squared as the second order derivative. So we can find the second order derivative for calculus of several variables too. So for that we have 4 second order derivatives. So the first one is differentiating this function with respect to x. So when you do that, I have d2z ds squared. And we can also differentiate this with respect to y. So we have d2z dy squared, so like this one's. Then since this is a function of s and y, and this is also a function of s and y, we have to differentiate this with respect to y. We call that cross partial derivative. So we have to differentiate this with respect to y, then we differentiate this with respect to x. So we have d2z dy ds, then we have d2z ds dy. So according to one mathematician called Young, these two partial derivatives are equal. So d2z dy ds is equal to d2z ds dy. So if we differentiate dy ds with respect to y, so dz ds with respect to y, if we differentiate dz dy with respect to x, it should be equal. So we have to use that example to verify that. Okay. So from example 3, we already have dz ds to be equal to 4y cubed s minus 10y plus 2. Then we have dz dy to be equal to 6s squared y squared minus 10s. So we are going to use this example to find the second order derivatives. So these are the second order derivatives. These are the second order derivatives. Okay, so first, let me clean this and write that one somewhere here. So let me write dz ds is equal to 4y cubed s minus 10y plus 2. Then dz dy is equal to 6s squared y squared minus 10s. So find the second order derivatives. So find d2z ds squared. So d2z ds squared is differentiating dz ds with respect to s. So d2z ds squared is equal to, so we are differentiating this function with respect to x. So again, y becomes constant, right? So this holds in 4y cubed are constant. We are differentiating x. If we differentiate s, we get 1. Okay? Then minus, so there's no s here, so this will give us 0, plus there's no s here, this also give us 0. So in the end, this is just equal to 4y cubed. Then we'll find this one, the 2z dy squared. The 2z dy squared is differentiating this function with respect to y. Differentiating this function with respect to y. So s is constant in this case. We have the 2z dy squared. So this is equal to, so here 6s squared is constant. We'll differentiate with respect to y. So the law says 2 comes down, we have 2y, 2 minus 1 give us 1. We don't write y to the power 1. So we have 2s squared, as a 6s squared as a constant. We differentiate, we have 2y. There's no y here, so this is a constant, so we have minus 0. So this is just equal to, so 2 times this will give us 12s squared y. So done. Out of the 4 we have done 2. Okay. So the next thing we'll do is, remember when we have z is equal to this function, we differentiate it with respect to s to have this. We differentiate the same function with respect to y, and we have this. So when we want to find the second order derivative, we have to differentiate this function with respect to s, that is this, and we have to again differentiate this function with respect to y. Then when we come to this one, we have to differentiate this with respect to y, and again differentiate this function with respect to x. So that's why we have the 4 second order derivatives. Okay. So here we've already differentiated this with respect to s. That's why we hold y constant to get this as a constant. We differentiated s and we had this. Then minus. There's no s here, there's no s here, we had 0, 0. Okay? So now we are differentiating this function with respect to y. This is how we write it. So we have the 2z dy ds. And this is equal to, so since we are differentiating with respect to y, s is constant. So we have 4s as constant, then y cubed. So we are differentiating y cubed. So 3 comes down, we have y, then we have squared. Minus, remember we are differentiating with respect to y. So we differentiate this. This is minus 10. So minus 10, we differentiate y, we get 1. Plus, there's no y here, so this will give us 0. So this is equal to 4 times this. We have 12s y squared minus 10. Then we have to differentiate this function with respect to x. Okay? We have to differentiate this function with respect to x. So write it this way, so we have the 2z dx dy. This is equal to, and since we are differentiating with respect to x, y is constant. Okay, so we have 6y squared as constant. We are differentiating s squared. So 2 comes and have s. 2 minus 1 will give us 1. So we have this. Minus, we have 10. We differentiate s, we have 1. So if we want to simplify this, so we have 12 y squared s minus 10. And this is the same as this. Okay, so we have 12s y squared. So 12s y squared, multiplication is commutative. So this is the same as this, which confirms Young's theorem, which says that the cross partial derivative function are equal. So, should I do another example? Yes. Okay, so that's the derivatives. So partial differentiation. Partial differentiation. Awesome. So now